Hello, welcome to Analysis of Algorithms, which we will shorten to AOA from now on. I'm Andy Ying,
And I'm Alex Liu.
will be your instructors for this class, and with our first lesson, we'll be covering big O notation and algorithm efficiency. This is a brief overview of the topics that we will cover today, so feel free to pause if you want to go through them.
The first thing that we'll go through is the concept of efficiency. So, in computer programming, efficiency can mean how much time something takes, how much time something takes to write, or the amount of resources, usually in the form of random access memory, that an algorithm takes to run. So, we generally prefer algorithms that are faster or algorithms that use less storage because storage and time are both limited. So, in order to do that, we need a way to essentially measure how complex every algorithm that we have is. So, for an example, if algorithm 1 takes 50 seconds and takes 10 megabytes of data to run, we can classify that. And if algorithm 2 takes 25 seconds and 20 megabytes of data to run, we can also classify that. But it'll hard to tell which one is better, which is why we use a certain notation to mark how things grow as they get bigger.
As Alex said previously, efficiency is really important because our computers do not have unlimited processing power or unlimited memory. Therefore, there is an incentive to implement only the most efficient algorithms to complete the tasks that we want to be done, as they can save time and storage that can be utilized for other tasks. For instance, think about our search engines such as Google. If the algorithms used in our search engines were not optimized and efficient, searching would be a lot more tedious and taxing on our computers.
Okay, so let's look at one example. So if we were to list numbers in increasing order and we wanted an algorithm to basically sort an array until the array is in increasing order, then one way to do it would literally be to randomly sort the numbers every single time and check if the order is correct. And if it is, we're done. So that's an extreme case, but you get the idea that some algorithms are just simply not efficient, time wise or memory wise, which is why you should probably have some quantitative way to describe how efficient an algorithm is. So,
The official notation that we use to measure an algorithm's complexity and how it grows with input size is big O notation. Below, we have a visual graph that shows how fast certain orders grow relative to others. Notice that with factorial and exponential growth, complexity grows quite rapidly, while, for instance, something with logarithmic complexity grows quite slowly.
right. And moving on to our first example, let's say our algorithm is the following: x equals 5 plus 10 plus in parentheses 15 over 3. So this would be constant time or big O of 1. So that means that no matter how large the input, and notice in this case there's no specific input, the algorithm will always take a constant amount of time to run. Now, this doesn't mean when I say O of 1 that the algorithm will take 1 second or a millisecond to run. It has nothing to do with how fast the program runs. It just signifies that this algorithm will not grow in time or, in this case, space complexity also as the input increases with size.
All right, so we've gone over an example of constant time complexity. Now let's go through an example that involves a linear time complexity. So here we go through an array of integers and we add 5 to each one. The runtime would increase linearly with input size because every time you add an element, you add another operation that needs to be done. Here we have a generalized linear function of a times n plus b, where a and b are constants. Note that the function clearly does not grow with a one-to-one relationship to n, but it still grows linearly. this means that the algorithm has a time complexity of O of n.
And notice how in the previous slide we ignored the constants and coefficients when calculating time complexity. And this brings us to some of the big rules of big O notation. So the first one, we ignore constants. That means constants not only on the lesser growing terms, but also on the highest term. And second, we always take the highest order term. So that means whichever n will grow the fastest. So for example, n factorial will grow faster than n cubed, or n squared, which will grow faster than n log n, which will grow faster than n, which will grow faster than just log n, which of course will grow faster than constant time.
Here is an example of the second rule that we've just gone over. So the first line of code has a time complexity of O of 1, while the second section of code has a time complexity of O of n. Since O of n is greater than O of 1, the time complexity is ultimately O of n and not of O of n plus 1, since the n term dominates and we just ignore any terms that are smaller.
Right. And as we've stated before, the term inside of the parentheses approximately represents how fast complexity grows with input size once n gets large. This term is based on the worst case scenario, which we'll discuss later in the next slide.
All right, let's look at this example. So right here, we can tell that this algorithm has a time complexity of O of n squared, since we see that one case leads to O of 1, another case leads to O of log n, and one leads to O of n squared. Since n squared is the highest order, that becomes our official complexity. However, that's only the case for x equals 1, which means it's not necessarily representative of the algorithm's performance overall. Likewise, O of 1 is the best case scenario, but generally the best case scenario, as its name implies, is best case and not practical. Now, this is where we would look at the average case of an algorithm, or how well an algorithm would run for most of the time. This is particularly useful in algorithms that we will cover later on. And when we really look at this algorithm, the average case would end up being O of log n, since roughly half the time it will be O of log n, the other half the time it would be constant. Log is greater than constant, so that would be our average case.
Yeah, so that is to say, while the algorithm overall might be O of n squared, the worst case might not be the best thing to go by. So let's look at another example. So here we have some pseudocode, which is just a simple loop that runs a certain number of times. And we see that every single time while x is greater than 1, it will keep dividing x by 2 and then printing out x. So if you want to figure out what the time complexity is here, you'd try to see what the looping behavior does as x gets larger. So for instance, if you were to input 32, the loop would run 5 times, and as log of 32 equals 5. So here, the log base doesn't really matter. We always just write O of log n, and we can see that this isn't like a linear pattern because you are exponentially decreasing n.
All right, so we've seen a lot of loops in the past, but this time we're going to nest them. So we're going to put a loop inside of another loop. Every time the outer loop runs in this program, so every time it runs once, the inner loop will run in n number of times. So the time complexity is O of n squared. If you remember from the graph shown from above, a polynomial time complexity grows quite rapidly and is not efficient, and if possible, avoid nesting loops together.
So to save some time, we won't be talking about algorithms with n times log n complexity, but this is mostly the target efficiency for operations like sorting an array, as ideally you don't want O of n squared, which will grow faster than O of n log n. So as the array input size gets very large, the time complexity grows basically like the linear function if you can look on the graph on the right.
All right, so now we've gone over a lot of examples of how to determine time complexity with examples of algorithms that lead to certain cases. But now we'll show how to calculate space complexity, or the amount of memory an algorithm uses to execute. The example here is just an algorithm that adds up integers, and this has a space complexity of O of 1, because the only thing that is stored is the input and the increment variables. So even when input size gets very large, these stay constant.
Now let's look at an example again, except this time we'll add up integers inside of an array. So for an array of size n, and some factor of n memory is used for storing that value. So the space complexity here is O of n. And if you have some outside knowledge of arrays, you might notice that arrays aren't exactly one-to-one linear with the size. But as we've already mentioned, we're just looking at like overall and we're disregarding any constant. So overall, the space complexity here is big O of n.
All right, so just to summarize our general rules and the examples that we've gone over, whenever we calculate big O, we first look at looping behavior, because looping behavior will give us a good idea if the time complexity is going to become polynomial. And then we take the degree of that. Generally, that's a good shortcut to determining your overall time complexity, because the higher polynomial order will always override the lesser ones once input n gets really large.
Right. So after learning so much about big O notation, you might be wondering what some uses for big O notation are. It turns out it has several useful applications. So the first one is limiting worst case runtimes in algorithms. Now you might think someone would care most about the average time, but if you're like a big corporation, you would want to limit the worst case time because you don't want any downtime due to algorithm failures. Second, we like to determine the efficiency of various algorithms, and usually we don't want like an actual function, which could be lengthy and hard to write out. And third, it's easy to communicate with others. So in like every CS job interview or when you're talking with other programmers, when you talk about big O notation, they'll understand. Fourth is it's not machine dependent. Like I said, if you have a really quick computer, you might run an algorithm 2, 3 times faster than someone else, but that's not really representative of how efficient the algorithm is. And big O notation helps with that by being hardware independent. And finally, it's simple and easy to use because almost anyone can understand the concept of big O notation and be able to grasp that some like n log n, for example, is better than n squared. It's very intuitive.
All right, with that being said, big O notation still has several limitations and shortcomings. It's mostly a theoretical model of how runtime grows when input size gets large. That's very important because when input sizes are not very large, coefficients and constants do matter, which means that algorithms with the same big O complexity may end up having wildly varying runtimes, especially when your input size is still quite small.
And to wrap up our lesson on big O notation, um, that was it. And we hope that you've learned a lot about big O notation and some of its uses. And in the next month for AOA, we'll be talking about searching and sorting algorithms, which we sort of touched on with big O notation, but you'll learn which ones are most efficient and their uses. So thank you very much for coming.